Today, we're diving into something amazing, compounds that are just as beautiful as they are essential. I mean, they're behind some of the most stunning colors you see in nature and some of the most crucial jobs going on inside our own bodies. So let's get right into it. So let me ask you a question. What do you think connects the deep red of our blood, the vibrant green of a fresh leaf, and the beautiful sparkle of a gemstone? It kind of sounds like a riddle, doesn't it? How could one single idea in chemistry possibly link all of these things together? Well, the answer is a really fascinating class of substances called coordination compounds. You can think of them like the secret architects of our world. And today, we're going to pull back that curtain and find out exactly what makes them tick. So here's our plan. First up, we'll see how these compounds literally color our world. Then, we'll do a bit of time traveling to meet the genius who first figured them all out, Alfred Werner. After that, we'll dive into the science of their invisible bonds and, of course, reveal the secret behind their gorgeous colors. And to wrap it all up, we'll see just how much these compounds have changed everything, from medicine to industry.
All right, let's kick things off with the chemistry that colors our world. I mean, why are these compounds so common? You might be shocked to find out you're interacting with them this very second. Just look at this list. Chlorophyll, the stuff that makes plants green, that's a coordination compound with magnesium right at its heart. Hemoglobin, carrying oxygen in your blood as we speak, that's one built around iron. Even vitamin B12 is a super complex cobalt compound. And those amazing colors in rubies and emeralds, yep, you guessed it, that's tiny bits of metals like chromium all tied up in these special structures. This quote really says it all, doesn't it? They aren't just some interesting topic in a textbook. They are absolutely fundamental, the true backbone of so much of modern chemistry, both in living things and in industry. So how on earth did we figure all of this out? Well, for that story, we need to go back in time, back to the late 1800s, to meet a scientist who is basically a chemical detective. This is Alfred Werner, and he was really puzzled. He kept seeing these simple salts, like cobalt chloride, sticking to neutral molecules, like ammonia, and forming these beautiful, stable, colorful new compounds. The problem was, nothing in the chemistry books back then could explain how this was possible. So he got to work in the lab. And his experiment was so simple, but just brilliant. He took these different cobalt compounds and added silver nitrate, which basically pulls any free chloride ions out of the water. But look at what happened. With the yellow one, poof, all 3 chlorides came out. The purple one, only 2, and the green and violet ones, just 1. This was huge. It was the clue he needed. It proved that not all the chlorides were attached in the same way. Some were held on super tight, and this led to his big aha moment. He proposed that metals have 2 different kinds of connections, or valences. First, there's the primary valence. Think of this like a loose connection. It's ionizable, which is just a fancy way of saying those chlorides could easily break off. But then there's the secondary valence. This is a super strong, non-ionizable bond. Anything attached this way is locked on tight to the metal, forming a solid, stable core. So Werner's whole theory really boils down to 4 key ideas. 1, metals have these 2 types of bonds. 2, the primary ones are weak and can break off. 3, the secondary ones are strong, and a metal always wants a specific number of them. And 4, and this was the truly revolutionary part, those strongly bound groups arrange themselves in very specific 3D shapes. This idea was so groundbreaking, it won him the Nobel Prize in 1913. Okay, so Werner's theory was a massive leap forward, but it was still a bit old school. It perfectly described what was happening, but it couldn't really explain why it was happening, at the level of electrons in quantum physics. I mean, it left some really big questions unanswered, like why are certain elements, especially the transition metals, so good at this? And why do the bonds point in such specific directions to make those cool shapes? And the biggest question of all, where does all that beautiful color come from? Werner's theory just couldn't tell us. So the next theory to come along was valence bond theory, or VBT. The idea here was that the metal atom takes its empty electron orbitals and kind of mixes them up, creating new hybrid orbitals. These new pathways are perfectly shaped to accept electron pairs from the surrounding molecules, which we call ligands. And this actually did a pretty good job of explaining those fixed 3D shapes. But VBT wasn't perfect either. It had a lot of assumptions baked into it, and it really struggled with explaining magnetic properties. And its biggest problem? The exact same one as before. It still couldn't explain the color. So to finally crack that mystery, we need to bring in a new theory. And that brings us to the really cool part, the secret of their color. It's time to talk about crystal field theory. Okay, now this diagram might look a little intense, but trust me, this is where the magic happens. Let's break it down. On the left, you see the metal's 5d orbitals. Normally, they all have the same energy. But when the ligands get close, their electrons start to repel the electrons in the d orbitals. The d orbitals that are pointing directly at the incoming ligands feel that repulsion the most, so they get pushed up to a higher energy level. But the other orbitals, the ones tucked between the ligands, feel less of a push, so they drop down to a lower, more stable energy level. This separation, this energy gap, is the whole secret. It's called crystal field splitting. So what we have now is a very specific energy gap. And the size of this gap is super important. It changes depending on which metal you have and which ligands are surrounding it.
And this is how that gap creates color. It's so clever. When white light shines on the compound, an electron from that lower energy level can absorb just the right amount of energy to jump up to the higher level. That right amount of energy corresponds to a very specific color of light. So the compound basically eats that one color from the white light. What we see is everything that's left over, all the other colors mixed together. And that's the beautiful complementary color.
Look at these examples. It makes it so clear. This cobalt compound here, it absorbs yellow light, so what we see is its opposite, violet. This copper complex absorbs red light, so we see it as blue. It's amazing, right? The color we see is literally the color that wasn't absorbed. And just like that, the mystery of the color is solved. So now that we've cracked the code on how these things work, let's zoom back out and see how these compounds have literally changed everything around us. I mean, the list of applications is just incredible. We use them to get pure metals, like gold and silver. They're used as powerful catalysts to make all sorts of things, like plastics. And in medicine, wow, some platinum compounds are life-saving chemotherapy drugs. They are everywhere, in almost every part of our modern lives. So just think about it. From the building blocks of life itself, like hemoglobin, to the sparkle of a beautiful jewel, these coordination compounds are shaping our world in ways we're still just beginning to understand. They are this quiet but powerful force behind so much of what we see and do. And that leaves us with one final, really exciting question. What future problems could coordination chemistry solve? Could we design a compound to capture solar energy as efficiently as a leaf? Or create new catalysts that could pull carbon right out of the air? The possibilities are absolutely endless. It really makes you wonder, doesn't it?